Hello! We will briefly look at the example of the matching game as a cooperative game. We will later apply this to the network bargaining game. Recall that the matching game consists of a graph G where the players are the vertices N, which is V of G. We also have non-negative edge weights W. The value of a coalition S is the maximum weight of a matching using vertices in S. As notation, for a matching M, W of M is the total edge weight of the matching. Here is an example of a graph with edge weights. The value of coalition AB is 3. There is only one edge that forms the matching. The value of coalition ABC is 6, the edge joining B and C. And the value of the grand coalition is 10. This is from the matching AD and BC. Recall that we interpret the weight of an edge as the value generated by the two players on both sides when they decide to work together. It is easy to see that this is a superadditive game, so we only need to consider the grand coalition when determining if it has a non-empty core. Recall that nx is in the core if and only if x is in script C, where script C is the polyhedron defined by x of n is equal to v of n, and x of c is at least v of c for all subsets C of n. And the problem of determining if a core is empty is reduced to checking whether or not script C is empty. Now, script C is a polyhedron that is defined by an exponential number of constraints. There are 2 to the n subsets of n. But we can make a simplification for the matching game. Define script C prime to be the set of vectors x where x of n is equal to v of n, and xu plus xv is greater than or equal to wuv for all edges uv, and x is at least 0. And our result is script C is equal to script C prime. So instead of checking that the inequality holds for every subset of the vertices, we just need to check that they hold for the edges. So here is our proof. If x is in script C, then x satisfies all the constraints in script C prime. We can take C equals to uv for each edge uv to get the inequality xu plus xv is at least wuv. And we can take C to be a single vertex to get x is at least 0. So script C is a subset of script C prime. Conversely, let x be in script C prime. Then x of n is equal to v of n. So the first constraint is satisfied. We now let C be any subset of n, and let M be a maximum weight matching in C. The goal here is to show that x of C is at least V of C, which is equal to the weight of M. We see that C consists of some matching edges in M, and possibly some vertices that are not in M. So x of C, which is the sum of all the x values of all the vertices in C, is at least the sum over all edges uv in M, x of u plus x of v. And this is because M is a matching, so no vertex is repeated in this sum. And for vertices not matched by M, their x values is at least 0 by assumption, so this inequality holds. And this is at least the sum over all edges uv in M, the weight of uv. And that is because x is in script C prime. And this sum is just the weight of M, which is the value of C. And that concludes this proof. Take a look at this example again from before. See if you can come up with a matching and a payoff for the vertices so that it is in a core. we had a maximum weight matching of value 10. So our payoffs has to add up to 10 and satisfy all the inequalities. So one possibility is 1, 4, 2, and 3. We can check some of the inequalities. XA plus XB is 5, which is at least the weight of AB, which is 3. XB plus XC is 6, which is at least the weight of BC, which is 6. And we can check that this is satisfied for all the edges. So X is in the polyhedron script C prime for this graph, so X is in the core with the grand coalition. One observation you can make is that the edges in the maximum matching are efficient. That is, XU plus XV is equal to WUV for all the edges UV in the matching. As an exercise, try to argue why this is true. Now there are examples of the matching game that have empty cores. Here is one example with a triangle. Now try and explain why this example has an empty core. We see that the value of the grand coalition ABC is 3. That comes from the edge AC. If NX is in the core, then XA plus XC is equal to 3. This implies that XB is equal to 0. Can you see why? So at least one of XA and XC is at most 1.5. Say it is XA. Then XA plus XB is at most 1.5. And that contradicts the inequality XA plus XB is at least 2, the weight of the edge AB. So the core is empty. We want to determine whether or not script C prime is empty. In the same way that we determine whether or not script C is empty, we will form a linear program. We can determine if script C prime is non-empty by solving the following LP. Minimize x of n subject to XU plus XV is at least WUV for all edges UV, and X is at least 0. The same argument from before will tell us that this linear program has an optimal solution, and script C prime is non-empty if and only if P has optimal value V of n. For example, this is part of the LP for our graph from before. Once again, I'll ask you to take the dual. We see that there is one constraint for each edge, so there is one dual variable for each edge, YUV. The objective function is maximizing the sum of WUV YUV for all edges UV. For the constraint, we see that there is one constraint for each of the primal variables, so we have a constraint for each U in N. Now XU appears in constraint in the primal for the edges that are incident with U. So in the dual, we sum over all the edges that are incident with U, their value of YUV. And this is at most 1, and Y is at least 0. And that is our dual. The dual for our example is partially written here. We see that vertex A is incident with 3 edges, so there are 3 terms in its constraint. So then script C prime is non-empty if and only if D has optimal value V of n. So what is the meaning of Y? Notice that if Y is integral, then all of its values are 0 or 1s. That's because each constraint is at most 1. For each vertex, the number of incident edges with value 1 is at most 1. So the edges with value 1 would form a matching. Maximizing over all the integral solutions will give us the weight of a maximum matching, which is V of n. If this is also an optimal solution, then we are done. P has optimal value V of n, and the core is non-empty. But we did not consider all the possible feasible solutions for the dual. And that is because y could be fractional. Take a look at the triangle example again. If we assign 1/2 to each of the 3 edges, then the sum around each vertex is 1, so it is feasible. So feasible solutions to D are generalized matchings. Now the maximum matching in this graph has value 3, but the sum of the weights of the fractional solution is 1/2 times 2 plus 1/2 times 2 plus 1/2 times 3, which is 7/2, and that is greater than 3. So the optimal value of D is not V of n. In this case, a fractional solution achieves the optimal value. This implies that we have an empty core. So as long as no fractional matching has weight higher than via n, then via n is the optimal value achieved by a maximum matching, and the core is non-empty. So this gives us our proposition. The core of the matching game is non-empty if and only if D has an integral optimal solution. For our proof, it suffices to prove that P has optimal value via n if and only if D has an integral optimal solution. For the forward direction, we suppose that P has optimal value via n. Suppose via n is equal to W of m for some maximum matching m. We define a vector y by ye is 1 if e is in M, and 0 if e is not in M. Then y is feasible for D, because M is the matching. And its objective value is W of m, which is equal to V of n. We now have a dual feasible solution with the same objective value as the optimal value of the primal. By weak duality, y is optimal for D, and it is an integral optimal solution. Conversely, suppose y is an integral optimal solution for D. Recall that the y values have to be 0 or 1. So let M prime be the set of edges E where ye is equal to 1. Then M prime is a matching with optimal value W of M prime. Since y is optimal, M prime must be a maximum matching. So the weight of M prime is equal to V of n. So P has optimal value V of n. And that concludes our proof. So determining if the core is non-empty is equivalent to determining if D has an integral optimal solution. Here are some results from combinatorial optimization that we will state without proof. When the graph is bipartite, D always has an integral optimal solution, so the core is always non-empty. For general graphs, it is more complicated, but there is an efficient algorithm to determine if D has an integral optimal solution. We will be using the matching game in the network bargaining game, which we will discuss in the next lecture.